and we will begin the presentation, but thank you. Thank all of you for joining us. Oh, Man Wong, thank you for coming. But just about 2 more minutes at 10 o'clock on the dot, we will begin this presentation. And it's nice to see people coming from all over the world. I see the UK, Jamaica, Spain, and of course, from the East, the Midwest, and the West Coast of America here. Canada, India. Thank you, guys. Okay, in about a minute. Hello, Patrick. Thank you for joining today. Hello, Onkar. I see you guys have found the chat box. Hello, Patrick. Well, thank you for joining us from Jamaica. I'm sure it's very nice and warm and tropical out there. You probably heard about what was happening here in the U.S. last week, but I think things are getting better for everybody here as well. Good morning, Bess. Okay, it is 10 o'clock, so I think this is the right time to get started. My name is Junior Choe. I am the Microwave RF Product Manager here at Berkeley Nucleonics. I have some special guests with me here today, our friends from Italy, Mr. Stefano Parma with Active Technologies in Ferrara, Italia. He is our partners in development for the Model 685 that we will be highlighting today. Hello, Stefano. And the real star of today's webinar is Mr. Claudio Bonizzoni. He is a quantum researcher.
Everybody. Thank you for being here.
Yes. He is a quantum researcher with the University of Modena in Italy. So again, thank you guys. Thank you all very much for taking the time to join us today. As I was mentioning earlier, we have people from all over the world, from Jamaica, India, the UK. So we really appreciate you taking the time out. We know that we're not all on the same time schedule. So let me get started here. I want to show you guys our agenda, kind of broken up on what we'll be talking about. Of course, I want to quickly talk about Berkeley Nucleonics, where we're from, how long we've been in the business, our product portfolio, especially with signal sources, since we are talking about quantum computing and the signal sources that are required in that application. Of course, we will highlight our new arbitrary waveform generator, the Model 685. I have a little diagram as well that will be a little bit more helpful in showing where these signal sources lie within the QC setup. And then our special guest, Stefano and Claudio, they will do some real-time demonstrations for us. Well, Stefano will be the actual person doing the demonstrations. Claudio will dive much deeper into QC application in itself and the type of signals that he requires in conjunction with the real-time demo. And finally, we'll have a quick summary, a Q&A session, a question and answer for some participation from our attendees here today. We want to get your thoughts, answer any questions that you may have. So that will be available for you at the end of the presentation. Now, some general comments here. This webcast will be recorded and a link will be emailed to all of our attendees today. All of you attendees will be muted until the Q&A session at the end. But if you wanted to ask a question during the presentation, feel free to go ahead and type that question into the chat box. We have engineers on hand that are in the room that will most likely answer your question in real time. But by chance, if they missed it or it may be a little, more technical, then we'll definitely get to that at the end of the presentation. Now, a quick bit of advice, you're not forced to do this, but for a better experience, a more immersive experience, you may want to expand the presentation window. If you look at the top right-hand corner of the slide screen, you'll see the 4 arrows pointing outwards. If you just click that, it'll get you into the full screen mode. Again, that might be a better experience for you. Now, I will remind you that the chat box is not private. All of the attendees will be able to see your questions, comments, or maybe inappropriate jokes. So please keep that in mind before you type anything into the box there. This presentation is definitely not classified. So once we have sent you the recording, you are more than welcome to send it to any of your colleagues. The length of this webinar will be about 1.5 hours. Knowing this, I want to make this a little more fun than what we have normally done with our webinars. So we came up with this idea to have some free prize giveaways. So throughout this webinar, you will see a word puzzle that'll pop up. I'm not going to tell you when, but when this word puzzle pops up, the first person to answer correctly, that correct answer into the chat box, will win a prize. So let me just quickly switch over cameras here to kind of show you what I have behind me. You can probably notice if you're looking at my screen or my camera that there are a bunch of boxes and equipment. And hopefully you guys can see this. These are the prizes that we are giving away, whether it's an arbitrary waveform generator, a handheld oscilloscope, a spectrum analyzer, all boxed up and ready to go, brand new units. I have some demo units to show off, but we want to make this as fun as possible. We would love your participation. So the first person to answer the correct answer into the chat box will receive that prize for that puzzle. Mia will actually send you a private message to get your shipping address, so we'll know where to send your prize. So let me switch it back. Okay. Oh, and as you can see at the final words there is USA only. My apologies to our international attendees here today. I found that it is quite difficult to export free equipment internationally. So we still encourage your participation. And if by chance you do win, we'll definitely think of a prize for you. We'll think of something. Unfortunately, it will not be any of these, but I'll come up with something good for you guys, and we will let you know. So please participate when you see the puzzle. So let's start diving right in. A little bit about BNC. We've been in the business since 1963, so a little over 60 years. We've been in the test and measurement business. Our corporate headquarters are located here in San Rafael, California. We have additional offices and facilities all across the world. So wherever you are located, most likely we have a local representative that can support you on our behalf. Now, today, we are a recognized leader in the microwave and RF industry, with our signal generators, synthesizers, dedicated phase noise testers. If you are using some type of microwave RF equipment, most likely we have a solution here for you. So again, thank you guys for joining. So our product portfolio for our signal sources. I won't take too much time here. Many of you already know about our solutions. And again, we are going to highlight our new AWG line. But just a quick reminder, we have very, very good signal sources from full-on signal generators. Let me just go ahead and get my pointer up here. So it's not a traditional benchtop enclosure, as you can probably already recognize. It's a very, very small form factor, the size of a lunchbox, I would say. But all the capabilities, the features, and the specs that you require are all there. The frequency models are broken up from the low frequencies going up to 6 gigs. We have our 845 right in the middle going up to 26 gigs. And if you need the best performance, the lowest phase noise and so forth, we have our model 865 that can get you up to 40 gigahertz. Now, the letters in red, the model 875, this is our brand new vector signal generator. I know many of you has probably heard about this before, since we have been talking about this for quite a while. But now we finally have this available for our customers, the low frequency models. So the frequencies are broken up from 4, 6, 20, and 40 gigs. The 4 and 6 gigs are currently available. I actually have a demo unit for your evaluation if you're interested, so please do let us know about that. Moving on to our multi-channel signal generators. This is very exciting as well. Spec-wise, it is very similar to the high-performing 865, but a multi-channel version. You can get up to 4 independent outputs per unit. As you can see, this is a rack-mountable 1U 19-inch enclosure. We have the frequencies broken up again, 6, 12, 20, 33, and finally 40 gigs. Each of the outputs can be configured to have different frequency maximums. And then our new 875, we will also have a multi-channel version of that unit as well. And they will all resemble the image you see here in a very small rack-mountable 1U enclosure. Now, if you didn't need all the all the features and specs of our benchtop signal generators, we also have frequency synthesizers available. Now, these are quite popular as well, especially just for a low phase noise stable CW source. And the single channel versions will come in a small module. Again, would be maybe the size of an external hard drive. And then we also have multi-channel versions of this as well, and that will resemble the same enclosure as the 855B. Now, the frequency ranges are broken up again. You either have a 20 gig or a 40 gig model available, and that is the 865-M. The 825-M is our new synthesizer that we have just recently introduced to our lineup. This unit goes up to 20 gigs, but the main spec here that is quite interesting is the frequency switching speeds. It'll be in the single-digit microsecond range. And if frequency switching is of importance to you, this may be a good solution. This may be a good start in terms of finding the best solution for your application. And finally here, although phase noise testing may not be critical within quantum computing applications, I still would like to highlight this really quick here, just so you are aware that we have a dedicated phase noise tester available for you as well. And if you are needing to test your signal sources or signal sources to make sure the specs are correct and you can validate, this is a great piece of equipment to do that for you. Now, we are going to focus on our AWGs today. And again, this is in conjunction, in collaboration with Active Technologies in Italy. Our lower frequency models are the models 675 and 676. You have a number of channels here, 2, 4, or 8 analog. You can get up to 32 digital. Sampling rate is 2.5 gigasamples at 14-bit vertical, still very good. Spurious free dynamic range is about -160. Now, the bandwidth is what really separates these two models. The 675 will have a 300 megahertz bandwidth. The 676 will get you 1 gig. The waveforms are all there for you. Sine, square, ramp, Gaussian, especially for QC applications and so forth. I also wanted to highlight the pulse generator function of our AWGs. Now, having sub-nanosecond pulses is quite impressive in itself. In this case, you have sub-nanosecond pulses, but also have programmable edges. You can set your rise and fall times at a minimum of 800 picoseconds. Again, quite impressive for a pulse generator in itself. This is just another feature as part of our AWG solution. Now, the unit we will be highlighting most today is the Model 685. The functionality is still very similar as what you just saw with the 675 and 676. A full-on AWG with all the different waveforms. You have 2, 4, or 8 analog channels, 32 digital. This is where it will start to break off, sampling rate and resolution. 6.16 gigasamples at 16-bit vertical. Technically, this will make it one of the fastest, or the world's fastest, arbitrary waveform generator. We're very, very excited about this. The bandwidth on this unit is 2 gigs, but Stefano will dive into this a little bit more as there are some updates being made to increase this bandwidth, especially with the new RF mode feature. And again, Stefano will have a great demonstration going over that. Amplitude, 5 volts peak to peak into 50 ohms, a ton of memory, and another great feature, serial data pattern generator. This is something, again, that's not quite a standard with many AWGs. And the demonstration that Stefano will give you will dive a little more into that. And if you have any specific questions, please feel free to reach out to us directly. We're happy to support. Okay. So, I myself am not an expert in quantum computing. I'm not going to even pretend to be. But I understand that not every one of our attendees here are QC experts as well. So, I just have a basic question here. What is quantum computing? And try to explain this in layman's terms. So if you can imagine an ordinary computer chip, that uses bits. Many of us have heard of that, 0 and 1. These are like tiny switches that can either be in the off or on position. If you're in the off position, it will be represented by a 0. If you're in the on position, it'll be represented by a 1. So for every app you use or website or digital photograph you take, that will be ultimately made up of millions of these bits in some combination of 1s and 0s. Now with quantum computing, instead of using bits, we're using qubits. So instead of being either in the on or off position, qubits can also be in a state called superposition, where they're both on and off at the same time or somewhere in between the two. The other thing that qubits can do is called entanglement. So if you can imagine 2 coins, and if you flip one coin, you flip the other coin, those results are independent, right? One can come up heads, the other can come up tails, and that's it. That's your results. They're independent. But with entanglement, 2 particles are always linked together. So if you can picture those 2 coins again, if you flip one and it comes up heads, the other one will also come up heads. And that's amazing. That's very interesting. And the main reason why we are even focusing on quantum computing, why are we even talking about this? Well, we believe that this is the wave of the future. Pretty much every industry can benefit from quantum computing. It is still quite new in the stages. We've only unlocked a fraction of the potential. There's so much more that can be done. And recognizing this is something that we are excited to be a part of, especially being able to provide, high-performing solutions for your specific QC applications. Now, I have some industries here that are listed that could benefit. Of course, the list can go on and on. But one very easy example to think of is Google, right? And their self-driving cars, right? With QC in the future, you would expect that the development of self-driving cars will exponentially increase. They'll be able to, have much better solutions in the future using QC, right? Better batteries for your electric car, right? We want longer range now, right? We want to ease that range anxiety. Using QC could potentially have some much better performing batteries in the future. And the list goes on, solar panels as well. Only 10% of that, the sun energy that solar panel had captured actually gets converted to electricity, and the rest, that 90%, gets dissipated into heat. So using quantum computing, possibly solar panels will be much more efficient in the future. Maybe it goes up to 50%, and you can produce much more energy for yourself without dissipating so much more heat into the environment. But as mentioned, pretty much every industry could benefit from quantum computing. We're still in the early stages, but we do expect that within the coming years, many more advancements will be made, and you will see the benefits of artificial intelligence very shortly. So with that said, let me just quickly go over a diagram of what a QC setup could look like. I really want to focus on the actual signal sources, right? So if you can take a look at the middle here, this is where the signal sources lie, right? We have the AWGs that are necessary for your baseband IQ. You require multiple different waveforms, and many times you need the Gaussian waveform. With our Model 685, that is there for you. You can get in that baseband frequency of about 500 megahertz, be able to set the IQ channels and send that signal to the mixer, and then to the refrigerated chamber where the qubits lie. You excite those qubits, and then that signal will be returned to the digital readout. But at the same time, along with this AWG, you need some local oscillator signals as well. And the signal generators and the synthesizers that I showed you before, they can fit into this category. The only category, obviously, that we cannot provide a solution for is the digital readout. So, that's just a very basic diagram to give you a better idea of where the sources lie. But again, Claudio is the expert. We are going to lean on his knowledge, his expertise. With that said, I am going to, before I turn it over, my apologies here. Right after this, I will turn it over to Claudio. But I'm very curious to know where all of our attendees, where their responsibilities lie within quantum computing. Is this, a major part of your responsibilities today? Are you working in a QC lab, or are you more interested in the theory or the algorithms, or is this, just out of general interest? Either way, we would love to know out of curiosity, and maybe be able to support you a little better in the future, knowing how this affects you. So with that said, I'm going to go ahead and pop up the poll. It'll just take me a quick second here. And I would say I'm just going to give it maybe 30 seconds. If you could just take a look really quick, take a moment to, wow, okay, it's going off. It's going off. I see the numbers are shifting. And after about 30 seconds, I will go ahead and show everybody the results. Thank you, Sergio. If you wouldn't mind clicking that in the poll as well. I'll give it maybe 10 more seconds, and then we'll show the results. Okay. Environmental impact. That's very interesting. All right. So, I still see a few more clicks here. I don't want to take too much time here because, as I mentioned earlier, it's going to be about an hour and a half with all the technical information that we have for you. But this is very interesting for us. It helps us support you better, knowing, what really matters to you with QC. So I think that's about good. Let me go ahead and end this poll. Thank you guys all for participating. Going to end it. Wow. Wow, I'm very surprised at the other. Let me go ahead and share this with everyone. Hopefully you guys can see. So, and it makes sense. Majority is in the electronics, right? Theory, very interesting. Algorithms, wow, okay. And other. So, yes, if you clicked other, we want to know more specifically. I see that many of you are going and typing in that answer in the chat box. Thank you for that. And we may reach out to you in the future directly to hopefully get some more feedback from you and learn a little bit more how this can be of help to you. Okay, I'm going to go ahead and finish this up. Let's go back to the slides, and I will turn it over to Claudio. Okay, Claudio, the floor is yours.
Okay, thank you, Junior. So we are dealing with quantum computing, but the point is that quantum has a very more wide meaning in our field. In particular, we are referring in this case to what is called quantum technologies. As you can see from this map here, that is taken from this very, very nice work, we have a lot of very different physical systems that can be used in quantum technologies. The point here is to combine them into an hybrid approach, in which exploit the properties that are coming from more different systems. Very different means, as you can see here, very, very different in terms of energy that you can have here, or eventually also in coherence time that you have here, or eventually in the way you exploit their feature to couple them together. Very, very briefly, you can work with optics, so I mean excitation with energies that are in the visible light. You can also work with microwaves that are here between. And finally, you can also work with radio frequencies or mechanical excitation. So you are here, very, very low frequencies. The point that you can also span over very, very different lifetimes. We will see later what this time with this lifetime is. And the point that you also have strategies to couple them together, to combine them into an hybrid device. So the point is that we can exploit both single coupling mechanisms that are red arrows, or eventually also ensemble, that means collective coupling mechanisms. Here, in particular, for quantum technologies, we are specifically focusing about microwaves. So I just selected here 3 examples of quantum technologies that are working with microwaves. Here you can see superconducting qubits that are the one that I'm going to show you very, very quickly in the next slide. Then I selected also spin ensembles into quantum circuits that are the one that you see here. Here you build a circuit that is essentially microwave circuit that is coupled to an ensemble, a collection of spins in this case. And finally, another example are spin qubits in quantum dots. The point is to take an electric charge, for instance, you can think about an electron, and to confine it into a scale that is on the nanoscale. And this is achieved thanks to electrical potentials. So the point that all these technologies that you can build, that are real technologies that are still very, very widespread today, have one thing in common. The thing is that you can encode a qubit inside the level that you have in the systems. You have to think about energy levels. I will give you an example in the next slide. And you have a strategy to codify 2-level system that corresponds to the logical levels that you want to use for your qubit. They can be 0, 1, or as also Junior mentioned, a superimposition of both states. For instance, this one here, this 0 plus 1 divided by square root of 2, for instance. This is the fundamental unit that you use for quantum information. This is a very, very basic building block for the quantum computer. In particular, I'm just focusing a little bit more on superconducting qubits because these are the ones that are generally used for making quantum computers today. For instance, I just selected this example that is taken from IBM Quantum Processor. Essentially, here you have an electrical schema of the qubit that is a Joseph Johnson combined together with a capacitor, or eventually a more complex network or capacitors combined together with the inductances. And what you achieve in this kind of circuit is that you have this set of energy levels that is not equally spaced in energy. This is because this is behaving like an anharmonic oscillator. So the point is that since the levels are not equally spaced, you can use the lowest one, 0 and 1, because the other one are spaced different energy, so you cannot address them directly if you address this transition between 0 and 1. So the point now is that you can exploit these two levels for making the logical level of the qubit. Here you see just a picture in which you have the feed lines that are coupling to the qubit, that are these ones in yellow and green and red, the two capacitors that are taking the signal from here to the device, to the qubit, that are these blue rectangles, and finally here in the middle, very, very small, you see in this set the final device that is your junction that is behaving like a qubit. Here, the aim is to address this very, very small object with microwave pulses. So, because the operation is driven by microwave pulses. Now, I'm leaving the stage to Stefano, who is going to show you more features about the waveform generator for generating these pulses, of course.
Okay, thank you, Claudio. So a key factor for quantum computing is to be able to generate RF pulse sequences to have and preserve high fidelity, greater than 99%, and building a strategy for error correction. So general, for all those reasons, it is necessary to work with a high-performance AWG like it can be the Model 685 from Berkeley Nucleonics. And that allows you to create and generate in an easy way very long and complex RF pulse scenarios. So having a 6.16 gigasample sampling rate, 2 gigahertz of bandwidth, and 16-bit of vertical resolution are key features for high-time resolution quantum needs. And so you can also synchronize with multiple units, and that allows you to tightly control multiple sequences in different qubits. So let's move and let's speak about the key features of the instrument. Well, very quickly, the model is available on 2, 4, or 8 analog channels, and the sampling rate is 6.16 gigasample per second with 16-bit vertical resolution. It is the world's fastest AWG with 16-bit vertical resolution. So the bandwidth is 2 gigahertz, and the instrument has a unique feature because it has a output voltage range of 5 volt peak to peak with an hardware offset of 2 and minus 2.5 volt. It means that you can shift the output from 0 to 5 and 0 to minus 5. So you can obtain a voltage window of 10 volt peak to peak into 50 ohm and at full bandwidth. The waveform memory is up to 4 gigapoints per channel, and the instrument is able to generate not only analog channels, but also up to 32 digital channels. And it is equipped with 3 different user interfaces, a AWG user interface, an AWG function generator, arbitrary function generator user interface, and a serial data pattern generator user interface. As I said before, you can also synchronize multiple units. So you can obtain a system made of 32 analog channels and 128 digital channels fully synchronized. Then here we have a screenshot of a sine wave at 1 giga at 5 volt peak to peak. In a few minutes, we will see it with a live demonstration. And here you have a screenshot of a 5 volt peak to peak square waveform with 110 picosecond rise time. And we will see it later. As I said before, the instrument can work in AWG mode, so arbitrary function generator mode, and this is the user screenshot from the user interface of this mode. With this mode, you can easily create sine waveform up to 2 giga. The sampling rate is fixed, and you can create square wave of 5 volt peak to peak up to 770 megahertz. You can generate sine wave 5 volt peak to peak at 1 giga or 5 volt peak to peak at 2 giga. The jitter is extremely low. It is below 2 picosecond. The marker is programmable with the same sampling rate of the analog channels, and all it is based on what we call our improved DDS technology. But you can run the instrument also in arbitrary waveform generator mode, and these are the user interface that we will see in a few minutes. The sampling rate is variable this time, and as I said before, we have 4 gigapoint of waveform memory. The rise time, it is 110 picosecond at 5 volt peak to peak. So you can generate 5 volt peak to peak waveform with 110 picosecond. You can generate also digital channel. They work at 1.54 gigabit per second. And the instrument has 2 independent trigger input signals. This is the front panel of the instrument. And quickly, this is a touch screen. We have a 7-inch touch screen, so you can control it like a tablet. But it is also equipped with knobs and buttons, so you can also use the knobs and button. And here you can see the 8 differential analog outputs, because there is a differential model, but also a single-ended model. We have up to 4 marker outputs and the 2 independent trigger inputs. Then the rear of the instrument is this one. Here you can see the digital connector, and you can connect it to LVDS probe or to a LVDS to TTL probe that we can provide as option. And here you can see the reference clock in, the external clock out, external clock in, and so this connector from incoming signals. And here you have 2 SSD slots to store your waveforms. So let's make a live demonstration. The first example, I'm going to generate the pulses, rectangular and Gaussian pulses, with the true arbitrary waveform generator mode. As you can see here, one moment that I'm going to share my screen. As you can see here, there is the user interface of the instrument that is connected by remote to an oscilloscope with 13 gigahertz of bandwidth. Here you can see the user interface of the oscilloscope. And now I'm going to control the instrument by remote with the mouse, but everything that I will do now with the mouse, you can do it with your finger, because it is equipped with a touch screen, so you can control it like a mobile phone, like a tablet. I give you a quick description of the user interface. Here below, there is a command bar that contains several buttons to control the instrument. You can start or stop the instrument, send the trigger, turn on and turn off the channels, the marker and the digital outputs, access to the settings of the instrument, access to the waveforms that are loaded into the instrument, control the instrument by remote, and here more button, you can save a project, load a project, and so on. The most important part of the user interface is the upper one here, that is the sequencer. As you can see, the sequencer is made of different entries. You can add up to 65,000 entry, and each entry contains a waveform. You can select here the waveform that you can add, but you can also create your own waveform. And here below, you have a graphical representation of the entries that you have selected, and the entry parameters in terms of amplitude, voltage high, voltage low, number of repetition, and length in terms of points. Let's make a quick example. I select as first entry a square waveform, and I put the maximum amplitude 2.5 volt and minus 2.5. Then I set 5 repetition, and then I had another entry pressing this button here. I set the DC level to that acts like the pause, so 10 repetition, and then I need to make another entry, and this time I want to add a Gaussian pulse that can be very useful for quantum computing experiment. Let's introduce the same amplitude, 2.5 volt peak-to-peak Gaussian pulse with 5 repetition. Then I will add another pause that is a DC level with 10 repetition. And let's add another entry here. This time we are going to create an entry. So if you go here and press this button here, it will open another software that is the waveform editor. We provide the this full software as a standard option, and you can use it to create not only your analog waveform, but also your digital waveform. As example, I can select here the waveforms that I want to create. I press this button here, and I can select from different waveform here, sine, cosine, triangle, rectangle, and so on. Let's select a pulse. Let's set the amplitude, for example, 1 volt, the offset 0 volt, and set a very narrow pulse. And so I created a very narrow pulse. Now I save it as narrow pulse test 01, and save it in the waveform list. Now, the waveform that we have created is available and in this list, and you can add it in your sequencer. As example, we are going to select the narrow pulse here, and we can change also the amplitude at 1 volt, and I insert with 5 repetition, and I insert a last pause made of 10 repetition. Okay, the second channel will be left as is. If I press this button here, you will have a summary of the instrument configuration, and then I can run the instrument to start the generation. Now, one moment that I have to set up the oscilloscope, and I will be back to you in a few seconds. So, as you can see, here, the instrument is generating the rectangular pulses, the Gaussian, and the narrow pulses. This is our sequence generation. Okay, then we can move on to another slide. And now we have another example that is the AWG mode. So now the instrument will is loading the AWG interface, because on this mode, the instrument is working as an arbitrary function generator, like the one that you can use on your benchtop. And using this software and firmware, it helps you to create easily, in a few seconds, standard waveforms, and you can modify their parameters in a glance, and you can change their parameters runtime without glitches. So now the instrument is ready, and here below there is the same command bar that we have seen before. The functions are quite the same. And here you have the parameters, the waveform parameters. Here we have selected a sine wave, so we have amplitude, frequency, offset, and phase parameter. And here you have graphical representation of what you will be in the output with a summary of the configuration of the instrument. But pressing this button here, you can select between many different waveforms, from sine, pulse, double pulse, and you can also select the run mode of the instrument. That it can be continuous, modulation, you can generate AM, FM, PM, FS key, PS key modulation, make a frequency sweep, or generate your waveform for a number of times you set here. Let's make an example, create a sine wave with 5 volt peak-to-peak at 1 giga. Then I press the run button, and the instrument will start generating. Now I'm going to set up the oscilloscope, and I will be back to you. So, as you can see here, we have created the 1 giga sine waveform with 5 volt peak-to-peak. But I can also create, for example, pulses. Now let's set it to default. I can select, for example, pulse. As you can see, the instrument, we have different parameters like offset, duty cycle, frequency, phase, and so on. We can switch also this parameter to width and to period, and to voltage high and voltage low. As example, I can set a pulse from -1 volt to +1 volt at, for example, 100 megahertz. Okay, then, sorry, okay, and then I'm going, sorry, because I have to change here the duty cycle. Okay, and now I'm going to press the run button, and the instrument will start to generate the pulse. Okay, so you can see the pulse here on the scope. Now I'm going to change runtime the parameter. For example, I can change the width of the pulse. Okay, so I'm going now to change the width, runtime. Okay, and I can also change runtime other parameter, like it can be the rise and fall time. I'm changing the rise time, and the same way I can change also the fall time. Okay, I can also change runtime the amplitude. For example, I change here the voltage high, okay, or the voltage low. So this software is very useful to easily create in a glance waveforms. I can also add runtime the noise. There is a Gaussian noise that is done in hardware. It is not software, so it is a Gaussian noise that we can superimpose to the waveform. So now, as you can see, the waveform becomes noisier. Okay. There are other kinds of waveforms that you can create, but one waveform that can be very useful for semiconductor test, for example, is double pulse. As you can see, the instrument is able to generate two pulses that can be one positive, one negative, both positive or one negative. And each pulse here has its own parameters. So, for example, I can change the width of the pulse 1, and here I can change the amplitude, -1 volt, and the width of the pulse 2, 13 nanoseconds. Then I can run the instrument. And here you can see the two pulses. And the runtime, I can change, for example, the delay between them, like we have done before. So I'm changing the delay between the two pulses. And in this end, I can also change live the other parameters that we have just seen with the other example. There are many, many features on this software, but for this demo, we have a few time, so we can move on now to next slide. Okay, now back to you, Junior.
Hopefully you can hear me now.
Yes.
We're at the point for our first puzzle, the first prize giveaway. So again, thank you guys for your engagement here, your participation. Right now, I want to give away our handheld oscilloscope, the model P2016. I think it might be similar to what you see here. This is our demo unit. Of course, the enclosure is going to be blue. That's really just like a rugged, a rubber case that you put on it. So I'm going to pop up the puzzle. We'll maybe give about 30 seconds to a minute for the answers to come in. Again, the first person to answer the correct question into the chat box will receive the prize. Mia will send you a private message to get your ship to address and all that information. So, ladies and gentlemen, it looks like Claudio may have some technical issues. Hopefully he is back with us. I'm sure he's logging out and logging back in by the time we are done with the puzzle. So, ladies and gentlemen, are you ready for the puzzle? Again, the quickest person with the right answer will get this prize. Okay. 30 seconds to a minute. Whoever types in the correct answer first wins the handheld scope. This one's not that hard, I don't think. Aha, Jeffrey Reinhardt. And you know what? Let me also, I like some of these answers here. Let me also mention that it has to be the complete answer. You know, what's up with that is the answer. But I see what's that? That's what's up. That's actually pretty good, David Gassner. That's what's up. I could maybe accept that. But the first person who came up with the correct answer, let me scroll back up here. I had you a second ago. Jeffrey Reinhardt, you are the winner of our handheld scope. I haven't checked if you are international or not. I hope that you are in the USA. If you are international, I will think of another way to reward your participation here. But I will assume that you are from America. This is your prize. So thank you very much. I'm going to put this box to the side here with your name on it, Jeffrey. This is coming out to you. We will ship this out to you ASAP as soon as we get your ship to information. So please look out for Mia's private message to you. So yes, and keep your eye out. These slides will just pop up out of nowhere. Puzzle number 2 will be coming up within the webinar, and then puzzle number 3 as well. And these puzzles will start to get a little bit harder as we go on. So with that said, I'm going to hand the floor over to Claudio. I think he is back with us.
Can you hear me?
Fully functional. We can hear you. I'm glad that...
apologies. Unluckily, I had a problem with the connections of the department.
No problem.
I apologize for this. Okay. So, thank you, Junior. I'm back. Okay. So, now I would like to speak about a concept that is the Bloch Sphere. This is because, as I mentioned before, we have a qubit that is, of course, embedded into a physical system. The point is that we need to model it somehow to represent it in a very, very easy way, hopefully to better understand how this object behaves, also to have an intuitive picture of it. And this can be done through the Bloch Sphere. This is because you think of a qubit that is a two-level system, you will have, of course, what we call the physical quantization axis. That is the axis that is set here by Z. This set that gives you the state that are 0 and 1. The state that gives you what is the basis for expressing the superimposition of the qubits. Because everything you will do will be expressed as a linear combination of these two states. These states will be the basis in this case. And the combination is the one that you see here, in which you have these coefficients that are alpha and beta, that have to respect this sum rule that is related to the probability of finding a qubit in the state, as we will see in the next slide. The point is that this way, the thing that the Bloch Sphere makes very easy to understand is how to represent a qubit, because the qubit will be just a vector into the sphere, like the one that you see here. And the point is that the angles that is forming are related to these coefficients. So you can easily express a vector by looking at the angles, and so converting the angle to these probabilities. So every direction will correspond to a combination of different alpha, different 0 and 1. The other point is that when you manipulate a qubit, you inject microwave, and every manipulation can be thought equivalent as a rotation of the qubit, so of this vector, into the Bloch Sphere. Just to give you a more intuitive picture about that, now we have a very, very nice animation that Stefano will move for me. So this is a simulation in which we have the same sphere, the Bloch Sphere. The vector, the red one, will be the qubit. And so, as you can see, Stefano now is moving the vector, simulating a rotation, in this case, by an arbitrary angle at this point. And so what you see that if, as Stefano rotates the vector, you will see that the angles and also the probabilities of finding the qubit, the alpha and beta, are changing depending on which is the orientation of the vector respect to the axis of the sphere. So this is essentially what is going to happen when you inject a pulse or sequence of pulses into your qubit. In particular, as I mentioned, I said something about probabilities. Just to understand a little bit more this concept, I just selected an example that is quite simple, that is what we called Rabi oscillation of a qubit. This is because you have to think to a qubit and to initialize it into a state. For instance, start by initializing it into 0, 1. At this point, you drive it with a microwave field and let him evolve under this field. The point is that at this time, the probability alpha and beta will be time dependent. So making also the states, the whole state of the qubit, time dependent too. The point is that if you just look at an ideal situation, an ideal system, you will have an oscillation that is like the one that you see here in this picture. the blue one will be the probability of 0, so alpha as a function of time, alpha squared actually in this case, and the other one will be beta as a function of time, beta squared, that is the red one. If you start with 0, you will have that 0 will completely drop. The 0 state will completely drop to 0 here at this time, and at the same time, the red one will increase from 0 up to the maximum. So there will be a coherent oscillation between the two states, between 0 and 1. This of course is taken into a time that depends by your system and also by the microwave field that you inject, by the strength of the field that you inject. The point is that in this case, if you manage to measure your qubit along the axis, so you project this vector into 0 or 1, you will get just simply alpha or beta. And the point is that this quantity squared will get to the probability of finding the state 0 or 1 after a measure. Probability will be simply alpha squared or beta squared, and will be time-dependent probabilities. The point is that everything in this case was done considering an ideal system. So an ideal is just an insulated qubit, so a qubit that cannot exchange energy with the environment. In practice, of course, the qubit is embedded into a physical device. It's a physical device itself. So, and of course, it can exchange energy with the environment. So the point that we have to face with the 3 different relaxation mechanisms that are the one that you see here. The first one is the longitudinal relaxation. Then we have also the pure dephasing, and finally also we have the transverse relaxation. All these mechanisms are related to a different exchange of energy with the environment. The first one, the longitudinal, is related to the time that the qubit takes to relax back to the initial state, to 0, after any kind of initialization you perform on it. And this is what we also call T1. This is also the longitudinal time, that because it's direct on the longitudinal axis or your reference framework. The other one is the pure dephasing. The other one, of course, in the plane of the precession of the qubit, that is the XY plane, is the one that you see here. This is a lot of the coherence in the phase of the wave function, so in the phase of your qubit. And this is reversible. This can be corrected by using specific passive sequences, as I will show you later. The other one arises from the combination of both the dephasing and the longitudinal time. And the point that this one is very important because this is the one that says what is called decoherence. So this is the one that limits the lifetime of your qubit. So the lifetime of the information that you want to store in your qubit and you want to exploit in your qubit. So the point is this is going to be the most important one for the lifetime, also for the application in quantum technology and quantum computing. In particular, when you want to compute something, you have to perform a rotation. And this is what we called a gate operation. A gate essentially is a rotation of a qubit inside the Bloch sphere. As you can see here from this list, I just selected here rotations that are made for a single qubit, but there are some analogs also made for 2 qubits together at the same time that are called 2 qubits gates. The point is that the gates are the fundamental logical operation. You have to think in analogy for the Boolean operation that are typically performed in a classical computer. These are the equivalent but done in a quantum way. And these are realized by using microwave passes. Every pass you inject will correspond to a specific rotation angle that will be done in a specific time that depends by the duration of the pass, and also eventually also with a specific phase that you want to have in your system. Now I'm just leaving the stage to Stefano, that is going to show you more about how to encode this rotation into the waveform generator. So please, Stefano,
thank you,
the stage is
Claudio.
yours.
Thank you, Claudio. So we need this, to create rotation around the x-axis of the qubit and around the y-axis. To do that, we need to generate I signals and Q signals with the arbitrary waveform generator. In particular, the Q signal will be 90-degree phase shifted, and so in this way the rotation will be around the y-axis. So let's make the second example of this webinar, the second live example, and we are going to create I and Q baseband signals with the waveform generator. So now I share the screen, and as you can see here, we return in AWG mode, and here we open the waveform editor. In the waveform editor, we can also put the representation from samples to time, and we can select also a portion of this time. So, for example, you can select 6.5 microsecond, and we can select 6 microsecond. Okay, and we are going to create train passes with the duration of 500 nanosecond. To do that, we go to Edit Entry, Edit Waveform, and we go to select Rectangle, and here we type 110 cycles to obtain a frequency about of 220 megahertz with an amplitude of 1 volt. Then we press OK, and here you have the first train pulses. Now we can select 500 nanosecond, okay, and as top 1 microsecond, and we go here and we do the same thing we have done before. We type 110 cycles to obtain 220 megahertz, amplitude 1 volt. We press OK, and now we will do the last train of pulses. Let's put it around 12.5 microsecond, and start 12 microsecond, like that. Same waveform, rectangle, 110 cycles, and 1 volt amplitude. Okay, now we have to select the other channel. Let's make a DC level, so with 0 volt offset, and we are going to create other train pulses. Let's select the selection stop, selection 1 microsecond, and selection start 500 nanosecond. Okay, as same waveform, rectangle, same number of cycle, but same amplitude. But this time we need to change the phase because the Q signal must be 90 degree shifted from the I signal. So 90 degree phase. Press Enter and make another selection here at 6.5 micro and 6 micro here. Edit waveform, same waveform, same frequency, 1 volt amplitude, and 90 degree shift. Okay. So to speed up the creation, we can also don't do this one, and we can save the waveform in the TrueArb. Let's press Save in the waveform list, and so the waveform are saved here in the TrueArb software. Now they are available here, and we can load the first channel with the high signal, and we go to the second channel to set the Q signal. We select the Q signal. Okay, so now the instrument is ready to generate. We press Run, and I'm going to set up the oscilloscope. Okay. So, okay, so as you can see here, we have the 2 train pulses, the 2 sequences, the I and the Q signal. I can zoom in, okay, and they are 90 degree shifted. But we have also another feature that can be very useful because at runtime we can change the skew between the channel. Not only the skew, but also the amplitude. So there is a parameter here in the settings that changes the skew from channel 1 to channel 2. So you can change the phase shift runtime. If, for example, I put here 10 nanosecond, okay, you can see now in the oscilloscope that now they are phase shifted. But I can do it real time in this way. I'm going to change now in real time the phase shift between the two channels. And another thing that I can do, I can change in real time the amplitude of all the waveforms that are contained in the first channel, because there is a parameter called amplitude scales, and this allows you to change the amplitude scale, the scale of the first channel. So you can change runtime the I and the Q signals without needing to reload it into the sequencer. Okay, now, okay, I finished for this demonstration, and now we take a look to the quantum computing flowchart. As you can see here, we have a classical computer, and you can create your quantum algorithm on it. After that, the algorithm is translated here in control signals that will pass in electronics that are AWG, mostly are AWG and up converters. So the AWG will generate the high EQ signals that we have seen just now. The up converter will convert the high EQ signals to generate RF pulse sequences in the range of typically 3 and 6, from 3 to 6 gigahertz. These signals will follow this path here and will go to the dilution refrigerator and will reach here the quantum chip. The quantum chip will elaborate the algorithm and will give us a result. The result will be will pass here and will reach other electronics that will down convert the signal for RF to baseband. And then the signals, the result must be digitized in 0 and 1 bits, classical bit that can be seen by the classical computer. So you will have the result of your algorithm here, of your quantum algorithm. Then there is a new puzzle here. Junior, it's your turn.
I mute mine through the headphones here. You know, I don't want you guys hearing me breathe while you're speaking. So, yes, the next puzzle is here. This is for our arbitrary waveform generator, the model A2085, and obviously this is not even close to the specifications of the AWG that we are showing off today, but still could be useful for you. And this is basically what it looks like. If you can see the little screen with my camera, I'm trying to show it off. Now I have it already boxed up, a brand new unit ready to go right here. Are you ready for the next puzzle? We'll give you about 30 seconds for the answers to come in. And again, it has to be the complete answer. All the words must be there. So 3, 2, 1, go. This one's not so bad. I see many people are typing here. I believe the winner is Gabe. Although, Dave McKee, you wrote it very well, capitalized letters. I mean, that's if you're a Star Wars fan. But it looks like Gabe is the winner. So, Mia will send you a private message. Get all your contact info shipped to address, and we will get this out to you ASAP. So thank you guys for participating. I have another one in here, so keep your eyes peeled. The last prize will be for our spectrum analyzer. So I will go ahead and push this through and let Claudio speak about the dilution refrigerator.
Thank you, Junior. Dilution Refrigerator is a commercial device that most labs have to cool down every system they want to measure. The point is that this is needed for quantum computing and for quantum computers because, as I mentioned, there are a lot of effects that can kill the qubit, so the qubit states. And the point is that all these effects come through very, very heavily. In particular, the first one, that is the most common one, is thermal radiation, that will induce a relaxation of the spin that is not the way that you want to have for preserving information. So first thing to do is to cool down at a very, very low temperature. So it's just a few millikelvin above the absolute zero. So this is required to work with superconducting qubits at the level that you need to require for quantum computing. And this can be achieved down inside these machines that are essentially refrigerators. Of course, in this case, you have a lot of stages that are the one that you see here horizontally. Every stage keep a very different temperature from the top to the bottom. So from room temperature that is outside of this one down to the working temperature that is the one that you reach here in this position, in this plate here. And the qubit will be in this position here, essentially. The point that, of course, you also have to close everything to a box, specific shielding for electromagnetic radiation and also from the environment, to screen everything from the environment. Of course, this is not the full device that is in working configuration. Moreover, you also have to add all the connections to bring the microwaves from the external down to the 15 millikelvin stage. This is done through this connection that you see here in vertical. Every connection goes through the cryostat, reaching the part where the qubit is placed. Of course, the working frequency is dependent by the qubit, but in this case can be around 6 gigahertz, maybe from 5 to 7 gigahertz, but on the order of few gigahertz. Finally, just taking a close look to the quantum processor. Here you can see this image about the processor that was developed by IBM maybe a few years, not very, very recently, maybe. But this is the simplest one that allows you to understand how a quantum processor basically is made. The points that you see here that is hosting 5 qubits, that are the red regions that you see here, here, and also here and here. And these qubits are connected to a network that is essentially based on resonators. Those are planar resonators that are the devices that you see here in blue, also in yellow and in green. Everything is needed because if you want to inject the microwaves to the qubit, you need to bring the signal down to this level. But the qubit is as a dimension that is on the order of microns, eventually even below micron. So the point is to couple it to the feed lines, so you need these geometries. Geometries are needed to bring the pulses there to manipulate the qubit, and also to read the state of the qubit at the end of your quantum operation.
Okay.
Now,
thank you,
Stefano, again.
Thank you. So this Flowchart recaps this one, and we have here the quantum algorithm, then a block that represents the control signals that are typically made on Python, Livio, or using the user interface. Then the control signals are translated in baseband signals by the AWG that generate the I and Q signals. These signals will reach the mixer and up converter that will up convert the IQ signals and will generate the RF pulse sequences at 3 or 6 giga from this frequency range. They will reach the quantum chip, then it will give us a result that will be down converted, digitized, and so it can be it can reach the classical computer and they can read the result on your screen. Well, there is a preview during this webinar because in a few months it will be ready a new mode about the model 685 that is called RF mode. On this mode, the instrument will work no more at 6.16 gigasample, but at 12 gigasample per second, and you can create RF signals up to 6 gigahertz. It means that you don't need any more the up converter, and you can directly generate the RF pulse sequences using the model 685. So these RF pulse sequences will reach the quantum chip, and so you will have the result. So let's analyze more in depth this mode. It is a preview, so I can give you this number. The sampling rate will be 12 gigasamples per second. You can generate up to 6 gigahertz RF signals. On one entry that you've seen before on the sequencer, you will not insert one waveform, but 4 waveforms. These waveforms will be I0, Q0, I1, and Q1. And they will be internally multiplied by the sine of F0, cosine of F0, or by sine of F1 and cosine of F1. It means that at the output, you can use both of them, so 2 waveform mode or 4 waveform mode, and you can have an RF pulse sequences from 3 GHz to 6 GHz. It means that mode means 2 things. The first one is that you don't need anymore the up converter, so you can save from external hardware, and you can double the number of the qubit tested with a single instrument, because commonly you need 2 arbitrary waveform generator channels to test the qubit, because one output we need to generate the I signal and the other one the Q signal. Using this mode, you need just one output to test 1 qubit. So with a 4-unit system like this one, made of 32 analog channels and 128 digital channels, you can test up 32 qubits, not 16, 32, with a 100 femtosecond of skew resolution, and you can change the delay between the channels in real time. I have a few screenshots about what it will be the user interface. It will be this one. As you can see here below, we have 4 waveforms on each entry. The picture can see you 3, but they are 4 here on the bottom. And here we have a preview of a spectrum analysis. Here we have generated a signal at 3 GHz. And here we have generated a signal at 5 GHz. So they are RF signals of 3 and 5 GHz. So, Claudio, it's your turn, please.
Yes, thank you, Stefano. So I'm moving now to a slightly different topic that is related also to quantum technologies, because the point that I mentioned before, superconducting qubits are very important, but you can also encode qubits using collection of magnetic system in our case, so that are spin ensembles. So instead of using one single quantum object, you will have a collection of objects that behaves in a coherent way. So as a unique wall equivalent object. This is achieved generally at the microwave frequency, working with what we call electrosphere resonance techniques that can be achieved both in 3-dimensional cavities, so 3-dimensional microwave cavities, or eventually by coupling the same collection of spins on a microwave chip. Just a resonator that is not a 3-dimensional volume, but just a planar device that is made on a 2-dimensional surface. So just a chip in this case. Of course, that depends by the application you have in mind. Also, depends also by the scalability you want to achieve with your system, and also to the sensitivity you manage to achieve when reaching the spins. I just have to say that before continuing that our techniques are focused, of course, on electrosphere resonance. That means exploiting for this kind of manipulation the electronic levels given by the system. But the point is that all these techniques can be done also with the proper modification, the proper adaptations, of course, also to the levels that arises from the nuclear spins of the systems. So in the techniques that are nuclear magnetic resonance techniques, that of course are done not at the microwave regime, but at the radio frequency regime with RF signals. I'm not going to give details about the nuclear magnetic resonance, but more of the techniques can apply also to this case with the proper modification in the setup or in the sequences. Simple manipulation you can achieve with spin ensembles is the one that is called Hahn's-echo. Now we are sharing the screen from Stefano because we have an animation that is explaining to you better what is an Hahn-echo sequence and what is an Hahn-echo. That is the one that you see here. The animation is the one that you see here. You have to think that the spin essentially first is in thermal equilibrium, so it's not preceding. You have to initialize it and start the precession with the first pi half pass. It is the one that you see here. That's the one that brings the magnetization of the ensemble from the vertical axis or the magnetization axis to the plane of the precession. It is the XY plane of the Bloch sphere, as you can see here. The point is that the spins are facing with a very, very homogeneous field, so they're proceeding, but in a very, very homogeneous environment. That gives what I mentioned at the beginning to be the phasing in this case. So the spins essentially are losing the coherence, the phase coherence. So the signal will drop off very quickly without preserving the information. But as I mentioned before, this can be corrected. So what you can do at some point after a delay that is tau, you can apply another pass that is the one that you see here, the pi pass. So this essentially will reverse the precession of the spin. So in a way that after another time tau, the spins will refocus again, giving what we call an echo. And echo is the one that you, for instance, see here on this photo that was taken in our lab here in Modena. So having this kind of echo means that the system is behaving in a coherent way. The point is that, of course, in neutral-spin resonance, the technique, the basic technique, make use of rectangular passes that are essentially the one that you see here, as I showed you in the previous slide. Rectangular because in this case, the envelope of the pulse, the envelope that is the one that you see here, the envelope of your carrier frequency, is just a rectangle. So essentially is 0 and then maximum, so 1 in this case. So just on and off and on. But the point that you can replace this pulse with a more advanced one that is called Chirped pulse, in which you replace this carrier frequency here with another carrier in which the frequency is swept in time, and in particular is swept linearly in time, according to this relation. In particular here, the frequency now is time dependent. You see here the expression. You will have a bandwidth that is the one that you see here, delta omega, and also the duration of the pulse here. You can set the parameters by changing this one during the generation. This is going to be quite interesting for specific application where you need a larger bandwidth or respect to the monochromatic pulse that you might have in a single carrier frequency. And now I'm leaving the stage to Stefano, who is going to show you how to create a Chirp pulse with the waveform generator.
Okay, thank you, Claudio. Okay, now we're going to create a Chirp pulse with the waveform editor. And so let's move to the next live example. As you can see here, we have the arbitrary waveform generator interface that we call TrueArb. We press this button here to open the waveform list, and we need to run the waveform editor pressing this button. So the waveform editor will open now, and we can also load, for example, create a waveform from a formula. Now here I already created one for this test. Okay. And here, as you can see, there is the formula made of a sign of this value, where this number here is the frequency start, that is 200 megahertz, and this number here is the frequency stop, that is 500 megahertz. So, and this one, it is the duration that is about 500 nanoseconds. I press this button here, and so I've created our Chirp signals that we can use now in the TrueArb application. So, as example, I now am going to set to the Chirp here, and I'm going now also to add some pause in terms of repetition. So it can be, for example, 10 repetition to make a pause between one chirp and the other one, and then I can run the instrument. One moment that I set the oscilloscope. Okay, so we see here that we have our chirp. Okay, we have our chirp here, and there are other chirp, because here in the middle there is the 10 repetition, and I can also, for example, make a trend on the oscilloscope, and we can see the trend of the frequency that is 300 megahertz chirp waveform. Okay, so now I would like to also to insert, there is another way to insert the waveform into the sequencer. The other way is to use the import. So If you go here and press this button here, you can import from a TXT file some waveforms. So you can generate, for example, your waveform using MATLAB, Python, or LabVIEW, or anything as third-party tools. Save it in a TXT format, and then import it the point into the instrument. Okay, so the waveform has been imported correctly into the instrument. Let's insert it also in the sequencer here. Let's take this one. Okay, and then I can add another one that can be, for example, a simple one, a Gaussian pulse. I would like to make this example to explain you a useful mode of the sequencer that can be very useful to generate complex pulse scenarios for quantum application. We have seen here that we have the device settings. Now, the instrument until now has been run in continuous mode. Continuous mode means that all the waveforms in the sequencer are repeated continuously. But you can select also single burst. It means that all the waveforms are repeated for a number you set here. So all the waveforms here are repeated for a number you set here. Triggered continuous means that the instrument will wait for a trigger here before starting the generation of the sequence. Stepped means that the instrument will wait for a trigger before generating this entry. We'll wait for another trigger here and generate this entry, and we'll wait for another trigger here and start generating this entry. But the run mode that I would like to highlight in this webinar, it is the advanced mode. Advanced mode allows you to perform conditional and unconditional jump and go to instruction. In this way, you can build very complex pulse scenarios. So there is a new button here that is Edit Entry. If you press it, it will open the Advanced Editor. As you can see here, we have all the entry in the sequencer, and there are instructions. For example, for entry 1, we can decide to wait for a button that is a software trigger when you press this button here. A timer, you can wait for a timer that is internal into the instrument, or you can wait for an external signal that is trigger 1 or trigger 2. If we set button, when the wait event will arrive, the waveform will be repeated for a number of times that you set here. After that, you can decide there is a jump if instruction. So you can decide to jump for a button event, for a timing event, or for external signal event. If we select external, it means that when the event from external will occur, you can decide to jump to the next instruction, to the previous waveform, to the first waveform, last waveform, or to an entry that you set here. If, for example, we set 3, it means that when this event will occur, the instrument will jump from the waveform contained into this entry to the waveform contained into that entry. There are a last instruction that is a pattern jump. It is the same, quite the same of the jump, but on the rear we have a D-sub connector made of 8 digital lines. So here you can type a number from 0 to 255. If I put, for example, 125, when on this connector will arrive, will be sampled the number 125, you can decide to jump to the next, previous, first, or last waveform in the sequence. This allows you to change dynamically the execution of the entries, also of the waveforms and the pulse sequences that will be generated by your instrument, and can be very useful for your quantum computing test. Okay, then we can move to the next slide. And please, Claudio, the stage is up to you.
Thank you again, Stefano. Thank you. So now another topic that is quite common is what we call dynamical decoupling. Dynamical decoupling means that another way to correct the decoherence is to use a set of pulse sequences that are specifically designed to correct the environment that is using the coherence. The idea here is rather simple, because you have to think, for instance, here to have a distribution that is the one corresponding to the energy of your spin system in this case, or eventually or your qubit, and the point is that it is coupled to An environmental distribution is the one that essentially is contributing in killing the lifetime, so in destroying the state that you want to exploit for your quantum purposes. This coupling can be reduced, in this case, in a stroboscopically way by injecting a sequence of passes that are acting like a filter, more or less like a filter that is like in telecommunication. So they are essentially filtering distribution, making it narrower, or eventually also making it disappear completely, if possible, of course. This depends by the distribution and the filter that you apply. So in this case, the pass sequence that you apply on your system. The point is that reducing this distribution here, filtering it, we reduce the coupling of this redistribution to your spins. So we preserve the life of your system. So in this case, we preserve essentially the information that you want to use in your application. I have to say that literature, as you can checking dynamic decouplings, there are a lot of protocols you can think to exploit. For instance, I reported here one example taken from this review. This is a sequence in which we have a sequence of passes that are X, Y passes repeated in this pattern a lot of times in a cycling a lot of times. The point here is that this sequence can be rather complex and can be used for specifically correct specific distribution or eventually in specific environments. Here, for our webinar, we selected to show two specific dynamical decoupling protocols that are the one that you see here in this slide. The first one that is very, very common in electrospin resonance is the car parser AWG sequence. Other one is the uridynamical decoupling. Both sequences are essentially based on a first pi-half pass that is used to initialize the system and to start the precession of the spin. Then, for the car parcel, you have a train of equally spaced pi passes in time. In this case, an echo will occur in the middle of each couple of pi passes that you inject. Here, you can think to change all the parameters of the passes and also the number of the passes in your sequence. This n number of pi passes can be also very, very large. The point is that you collected the decay of the echo in a unique wall acquisition of the wall sequence that is performed with your instrument. The other one is quite different, is a little bit different because you started with the same pi pass here, and then you have a train of passes that is not spaced equally in time, but is spaced according to this relation here. It depends by the sin squared of n. N again is the number of the passes, pi passes, and j that is the index that codifies each of the passes in the sequence. The point is that in this case you have to select your t prime, that is the duration of the sequence, this one here, t prime. This we calculate, we give you a set of tj's, each for one for each pass that you have in the sequence, and then you perform the sequence, acquire at the end the echo. At the end, you will have to change this t prime again, calculate a new set of times, a new set of delays, and then apply again them to your system and collect a new echo at the end. So at the end, your experiment will result from the acquisition of different echoes taken at different t prime, so different durations of the wall sequence. This is another protocol that is quite interesting for, especially for applications which you use collecting excitations of spin ensembles for making quantum applications. I leave back the stage again to you, Stefano.
Thank you, Claudio. So we are going to generate with the model 685 these two sequences that Claudio already just explained. So we'll do it using the import file function. So now I'm going to share the screen, and as you can see, there is the user interface of the TrueR mode, and we are going to import the waveform. The first one is the car parser Mabon-Gill sequence that we have here. Okay, we press open and press webinar. We put a name on it, and we have been imported it. The second one is the dynamic decoupling sequence, so it is on this folder. Okay, name on it, and we press the OK button, and the sequence has been imported here. So now they are available on in the sequencer. So with this drop-down list, you can add it. We have loaded the first channel, and we'll do the same for the second channel. Okay, this is the second dynamic decoupling sequence. We press the run button, and the instrument will start generating. Okay, one moment that I set up the oscilloscope. Okay, so as you can see, we are generating the sequence that we are created right now with importing the function. So these are the two dynamic decoupling sequences that we have created. Okay, we can go on with the presentation, and so we can move to the next slide. And please, Claudio.
Thank you, Stefano. So the point is that, as we mentioned in all the seminar, one way to generate passes is to use IQ generation. So essentially the idea is to take a mixer, combine together a carrier frequency with a modulation that is given by the waveform generator. The point is that this is not the only way we have to generate passes, because another alternative that can be quite different is to use microwave switches. These devices that are the one that you see here, so they are very, very small devices on the order of centimeter dimensions, can be used to generate passes as well. The point is that here you have the same carrier frequency that is injected through a switch that is controlled by a signal that is given by the waveform generator. The point is that this simply will open and close the circuit, letting the microwave go through the setup, or otherwise to stopping the microwaves. So this will behave like just a switch, an electrical switch. This of course gives you less flexibility in generating the passes, because this is limited by the speed of your switch, and of course by the length of the pass and by the amplitude you want to inject. But here, the point is that with your waveform generator, you typically need high voltages to control the switches, because this is based on TTL levels, logical levels like TTLs, or eventually from voltages that can be even units of voltage. So the waveform generator that we presented might help in using these switches in a very, very easy way in generating passes. The other application that is quite important that I want to mention here is optical modulation. This is because in introduction I show you a picture with a lot of quantum technologies merged together in a unique map. The point is that I mentioned that you can exploit those technologies that are given by different energy scales, that works on different scales. As I mentioned, we have optical excitation, essentially with lasers, but also microwaves. Here the point is that if you want to combine together this excitation and to send them into the same sample, you need, of course, to control both the time at which you send each pass, also to synchronize you want also to synchronize this pass in the sequence, and also to synchronize devices that are very, very different. So this can be done easily by, for instance, connecting the AWG to both a microwave source to control the microwave, and at the same time to connecting the waveform generator to an optical modulator that controls the flowing or laser light through the system. Of course, this gives you a possibility to perform experiments like optical readout of magnetic resonance experiment, eventually also to perform quantum sensing with nitrogen vacancies, and also experiment which you want to study conversion between, for instance, in this case, optics and microwave frequencies. I just selected here one example that is a quantum memory that is working with nitrogen vacancies, in which you have microwave coming and flowing here in this part, combined together with a laser that is ejected here from the top, that is reaching the spin ensemble that is placed here. That is a nitrogen vacancy spin ensemble. Here you see another application that is based on sensing, in which you still have a microwave that is coming into a chip that is the one that you see here in gray, and you have a pumping that is injected here in this position from the top with a laser. Here, applications can be rather simple to implement, because in this case you can use a channel of the waveform generator for controlling the microwave part, as Stefano has already shown to you, and can use another channel to control the output that goes to the optical modulator. Okay. Now Stefano will show you better detail this application with the waveform generator. So please, okay. Stefano, go ahead.
Okay, thank you, Claudio. So as Claudio already said, we are going to generate on the channel 1 a sequence like we have seen before, and on the second channel we load a rectangular pulse of 5 volt peak to peak. I would like to highlight that this feature is quite unique on this kind of instrument, because the Model 685 is a high performance AWG, and it has a high voltage 5 volt peak to peak output range. So let's go to the live demo. And so here we have on the first channel the sequences that we have loaded in the previous example, and on this final example of this webinar, I'm going to load on the second channel in the first entry a square waveform here, and with an amplitude of 2.5 voltage high and minus 2.5 as voltage low, so 5 volt peak to peak. But I want to create a 0.5 pulse. So we have a feature that is called hardware offset that lets you to shift the offset of your output signals. And so we can do it in the channel settings. You can see here that for the channel 2, we have a baseline offset parameter. And if we set it to 2.5 volt, it means that on the output, it will be generated a pulse from 0 to 5 volt. Let's see it on the scope. One moment that I set up the oscilloscope. Okay, so okay. Okay, as you can see here, we have created the 5 volt peak-to-peak output pulse. Okay, then, okay, it is, okay, for this example, I finished, and this was the last live example for this demo. And now I would like to answer also to a question that I've seen here. But yes, the instrument, the Model 685, can be remote controlled, so you can you can insert it in your test bands because we support the following remote interfaces like LAN, GPIB, USB TMC, and we provide a full set of SCPI commands. And in this way, we can support Python, MATLAB. We will provide a full set of LabVIEW driver, C++, and .NET languages. In particular, I know that on quantum computer is very popular Python, and so we can support Python, with, for example, with Qcodes, Qtip, and Qd. And here you can see a screenshot from University of Modena that use Qcodes. And so this is all for the remote control. And I would like to quickly highlight the application, because now we focused this webinar on quantum computing. But for example, since we have generated I and Q signals, they can be used also for RF and wireless application for communication and defense electronics. But the instrument can be also used for big physics, for research in electronics, physics and chemistry, radar and LiDAR testing, aerospace and defense, test on semiconductor, and in all the fields where you need 5 volt with very fast rise time. And you can also generate a signal of real world, because you can generate almost any kind of signals using that instrument. Okay.
Yes, thank you, Stefano, and thank you, Claudio. That was amazing, highly technical information. Hopefully our attendees got some good knowledge out of that. This is our final puzzle. I know a lot of you guys have been keeping your eye out for it. This is going to be a little bit harder, but it is for the better prize of them all, a 3.6 gig spectrum analyzer, the model S1365. Now, I don't have a demo unit to show off in front of the camera, but that is an image you see. It's going to be very similar to the same form factor as the arbitrary waveform generator we gave away earlier. Again, nicely boxed up and ready to go. Whoever types in the correct answer first, again, will win this prize. Mia will get your information so we know where to send it to. So, are you ready? 3, 2, 1. There we go. Now, for me, this was a little bit harder, so I will give you guys a little bit more time. Nice try, Robert. Unfortunately, that's not the one. Sorry, Tim. Ooh, you guys are getting close. Every word has to be in there. Ah, William, I think it's you. I think you got it. Let's see. Let us see. That one's pretty good. Get the lead out. Metal rock band, lead rock band. Hang on. Lead rock and roll. Heavy metal rock band is the answer, as you guys know by now. Let me see who typed that in there first, though. William Kalfas. You look like you are the winner. Great job. Thank you for participating. Maybe I can dock you for misspelling, both lines there. You got band wrong and metal wrong. But we're going to be nice. You got the right answer. The spectrum analyzer is yours, so please give Mia your contact information, ship to, and we'll get this out to you right away. So that was our final puzzle, and we're pretty much at the end of our presentation. Thank you guys for joining us once more. I want to highlight our BNC Academy. Great for new hires onto an engineering team, maybe even students, young engineering students. No matter what department, we may have some pertinent information for you. In this academy, we're very excited about it. We've been getting very good feedback. We hope to continue to get some more feedback if you can take the time to take a look. I want to first give you your free code to access any of these courses available. I'm going to share my screen really quick here to show you how to get there. Hang on one second. I think it's because Stefano was sharing before, so I'm going to hijack his, and now I'm going to get to mine. So hopefully you guys can see this. Basically, this is our landing page for our courses, academy.berkeleynucleonics.com. You come to the front page, you will see all of the courses. You'll have the featured courses on top, but if you click on, show them all, we have a vast line of different types of courses, whether it's from nuclear detection technology, radiation detection, RF boot camp coming into the microwave RF field. This can be a good refresher if you're a seasoned engineer or if you are a student coming into the industry. A great tool for you. We have phase noise measurements, basic T&M terminology and fundamentals. But in relation to today's webinar, we have a quantum computing course, quantum computing with a focus on instrumentation. So your free code is Berkeley, just the word Berkeley. And the way to access that here, you just go to that, or the way to apply it, you go to the course itself, you click on that, you will be able to see the course curriculum. Everything is broken down for you, and then you can get started. Now, I think there's a little bit of lag. Hopefully you guys can see my screen and what I'm doing. It doesn't show me on the webinar, so I hope that you guys can see it. But basically, when you get into pay for the course, there's normally a $99 charge for any of these courses. There is a coupon code where you can enter, and there you just type in Berkeley. Yeah, I don't believe my share screen is working. There's a freeze there somewhere. But if you can imagine the credit card page, there is a little button to put in your code. You just type in Berkeley, and then it'll reduce your total cost to zero. And off you go. You can dive into any course, even if maybe you aren't an expert in nuclear. If you just have some interest, would like to learn a little bit more about it, that is there for you. The only thing we ask in return is that you give us a little bit of feedback, your thoughts on the content, any improvement suggestions. Again, this is something that we will continue to work on as the years go on, and we'd like to have a full-fledged academy with hundreds of courses in the future. So thank you again very much for your participation today, for taking the time to join us today. here is our contact information. Again, we will send you a recording. If you need to contact Berkeley Nucleonics with any questions, concerns, all of our information is right there. Our email, our website, our phone number, our address if you wanted to send us a physical letter. If you would like to contact Stefano, his email address is listed here. If you would like to contact Claudio regarding his application and his knowledge, his email is here for you as well. So this is the end. Thank you, everyone. We do appreciate it. And please let us know any questions, concerns, feedback. We are here to support you.
Thank you. Thank you very much.
Bye-bye.
Bye-bye.